Okay, I think we're going. Okay, so welcome everyone to this last Compute Accelerator Forum of 2021. So it's been quite a busy year. So just to, as usual, start with some very quick news. So first of all is just to advertise an HSF meeting next Monday, which is within the simulation working group. I'm advertising it here because this is specifically on the use of FPGAs for simulation, and the talk will be by Marco Balboni from Imperial College, and you may recognize Marco, who gave us a very good talk on development and FPGAs earlier this year. So if you're interested in FPGA use, and particularly for simulation work, then please attend this meeting. The link is there to the Indico page, and obviously Zoom links and so on. So back to the Compute Accelerator Forum. So today we're going to have two talks. The first from Attila, who's going to discuss the VecMem library, and then we'll have a report from Giovanni and Ricardo on GPU developments in the CERN's Beams department. So of course, this is the last meeting of this year, but we're already starting to plan and have our first meetings of 2022 scheduled, the first of which will be on Wednesday, the 9th of February. And we'll hear from the HEP CCE programs with two talks, one on portable parallelization strategies by Charles Leggett, and the second on fine-grained I/O and storage on HPC by Peter van Gemmeren from Argonne. So that's the first one. Obviously, if you go to the Indico page, we've already also scheduled one for March, but we're starting to fill out the remainder of the 2022 program. So as always, feel free to contact us if you've got any interesting topics that you'd either like to present or see us cover. We're obviously always welcome to hear of interesting subjects. And of course, this is the last meeting of the year, so we wish all of you a very happy Christmas and New Year, and of course look forward to seeing you all in 2022. And yes, I see in the chat, Sebastian, do you want to very quickly say something about this school?
Yeah, I'm sorry really for jumping in.
No worries.
It's the thematic CERN School of Computing that we're organizing several years. It was always focused on software efficiency, and since 2 years the focus kind of shifted to heterogeneous programming. Probably some of you or many of you actually are aware or even followed some of you this school, and we're just opening the applications actually tomorrow for the school, the next edition of that school in May 2022. So just I'm using this opportunity to advertise. Thanks a lot.
That's excellent. Thank you very much. We'll add that in the live notes as well, so it's recorded. Okay, so that's all from the introduction. So with that done, let's move on to our first speaker, which is Attila Krasznahorkay, who's going to tell us about the VecMem library.
Yeah, let me just bring up the slides. Okay, so I'll try to describe to you the development well, one of the developments that we've been doing in Atlas for the last year or so. But before jumping into that, so well, you can see some of the overview of I'll mostly be talking about memory management with heterogeneous computing, as you might imagine, because as it turns out, memory management is sort of it tends to be a key point in how well your application is able to run. At least from my point of view, one of the reasons that or the main reason why we need to be very mindful of memory management on GPUs is that in classical computing, when you are writing your application for a CPU, in the last several decades, hardware manufacturers became pretty good at hiding much of the complexity of what's going on in a CPU. Even though Intel and friends will still tell us how mindful we need to be about cache locality and how we do this in our code, and maybe even tell us that we should try to be even explicit about how we move data between different cache layers. But I can tell you, we never actually do that in, at least in HEP software. On the other hand, once you start writing some code for GPUs, you better be aware of how caching works on these devices, because otherwise you'll see orders of magnitudes of performance difference. So this is sort of where the whole thing starts from, that we need to be aware of this, but at the same time, the interfaces that all of these languages came up with, and all of these hardware manufacturers came up with, these are pretty much all C interfaces, C APIs, which I completely agree with them that it makes a lot of sense to provide a C API for managing memory and telling your application exactly what sort of memory you want to allocate, how you want to copy between memory areas, and so on, because this allows them to connect all of these languages to anything else. For instance, NVIDIA was very vocal in their latest conference about now finally providing Python bindings centrally for CUDA. And they can do this because, well, their basic API is a pure C API. But this also means that it's not that convenient to use in high-level C++, because now for quite a while, we've been teaching people to manage memory in C++ at a very high level. We pretty much advocate for not even using the new and delete keywords anymore in modern C++. We try to do everything through smart pointers and other types of techniques. So asking people to use something even a bit lower level with malloc and free style statements is possible, but it in my mind, it doesn't produce all that nice of a code base. And yet another reason why we do have to be very mindful of how we manage our memory is that device memory and allocating and deallocating device memory can be pretty slow. I myself was actually pretty surprised when one of our PhD students produced this plot that I didn't actually appreciate how much of a difference there is between just regular host memory allocations and in this case CUDA memory allocations. So this means that all of the things that we normally don't even have to worry about or not even think about in regular C++ code, of just creating an STD vector and not worrying about how it actually does the allocations, because allocations are pretty cheap. This is really not the case in device memory. So we need to try to be a bit smarter. Now, with all of this background on how we ended up here, well, we in Atlas, of course, have known about many of these issues for a long time. And we even wrote a couple of different implementations for like smart memory objects in C++ in the past. But about a year ago, when we started getting serious about writing a demonstrator project for running full particle tracking on GPUs with as realistic of a setup as we can. At that point, we once again wanted to visit this this topic of, okay, should we manage memory in this demonstrator project? Along with other aspects of this project, in the end, we separated this problem into its own repository. Here you can find a couple of links to some of the other things that that we are actively working on at the moment to put this actual demonstrator together. Now, the VecMem project, which at this point its main reason for existing is to serve this demonstrator project. It is a relatively small project. At least it's very small compared to something like the Atlas offline software, because it consists of a couple of libraries. Well, a core library that defines all of the basic interfaces and pretty much all of the container types that we use. And then we have separately libraries that implement the binding to the three main languages, the holy trinity of GPU languages at the moment. Now, the main thing that we are using in VecMem is a feature of C++ itself, and it's sort of an entertaining story. I believe that when we started developing this software, we didn't even know about memory resources at the start. We were ourselves actively thinking of how to make clever use of custom allocators in the STL, and sort of at the same time, or just like a couple of days before coming across this new feature in C++17, we pretty much came up with the same design by ourselves, that, well, we should really introduce some virtual interface for managing memory, because in the end, this is the main trick of this memory resource infrastructure in C++, that it allows people to implement like specific implementations of a pure virtual interface. Well, it's not quite pure. It's a virtual interface that allows some object to allocate and deallocate memory through this abstract interface without having to see that code directly, which is a bit different from the classical allocators in C++, which are purely templated. And from what I can tell, although documentation on this is a little bit sparse, all of this in the end seems to have come from NVIDIA. So this part of the C++ standard, from all I can tell, came mostly from NVIDIA, because they started using the same sort of organization in their own code not long before this arrived in the standard. Now, it is C++17, so you would think that it would be available out of the box pretty much with any compiler, but it's not quite the case. With GCC, you have to be on a fairly new version of GCC, but even worse is that with libc++, even with the very latest version, some parts of this this namespace are still not implemented yet. Still, it's fairly functional at this point. So, so how does it work? Just on a very very abstract level. As I said, this extension or this new feature in the C++ standard mostly just introduces an abstract interface, this std-pmr memory resource interface. Plus they introduced some custom allocators that make use of the memory resource. There are meant to be some standard memory resources in the standard library, but those are also pretty sketchy of what is available in various versions of GCC and Clang. And through this interface, you can, as I said earlier, you can sort of abstract away how memory allocation or deallocation would actually happen. And you can even do this in as complex of a way as you want, because the memory resource object that you implement, it doesn't even have to talk to a memory allocator and deallocator function directly. It is allowed to do its allocations and deallocations in as complicated way as it wants. And this is actually one of the key features that we make use of in VecMem, that instead of, for instance, implementing a caching allocator separately for CUDA and HIP and then for SQL, we just implemented a caching allocator on top of another abstract memory resource, because this sort of structure allows us to do this. And with this, well, we sort of came up with some nomenclature for this ourselves, although, well, this is really just something that we started calling these things, where we would call memory resources that directly talk to some other library or some language and ask that language for some sort of allocation and deallocation. We would call these upstream resources. While other types of resources that themselves don't actually allocate or deallocate anything, they just ask somebody else to do an allocation or deallocation, and then they put some additional logic on top of that. We would call these downstream resources. And we can do all sorts of interesting stuff with combining these types of resources. And just to give you an idea of what I mean, for instance, after declaring a memory resource for CUDA managed memory, we can just put an arena allocator on top of this. And as you can imagine, you could put this type of allocator or this type of caching on top of any other type of upstream memory resource. And then with this memory resource, we can start using STL types, because while the naming is a bit misleading, all of our host types, so things like VecMem vector, and as you'll see examples later on, VecMem jagged vector, these are really STL types. These are just convenient names for std vector itself. And we can also do all sorts of clever stuff, not just with managed memory types, but also separate host and device memory types, where the library does know how to explicitly make copies between the two. And this is really just to sort of give you a taste of how you'd express some very simple stuff in this language. Now, how we allocate memory and how we control the lifetime of device memory in host code is, of course, just one part of the problem. And interestingly enough, this is the part that most projects that I know about implemented. So if you look around, NVIDIA actually has many sort of overlapping projects in which they provide users with really smart memory allocation schemes and smart ways of managing the lifetime of memory allocations in host code. But what I found to be mostly missing from all of this is help with accessing this memory in device code. That sort of functionality I found really only exists in stuff like Cocos and Llama. All of the projects that coming from NVIDIA and co, those don't give much help with writing STL-like syntax in device code. So we just, bit our lips and we wrote a bunch of classes ourselves, which mimic the STL containers and are written such that they could work in device code. Now, one even more complication of this is that once we have these separate types for accessing memory and managing memory in host and device code, we also need some clear way of communicating between the two. And for this, we just ended up introducing a bunch of data types, where the most important part of this are these simple view types, which are really just plain old types. As you can imagine, for a vector view, it's pretty much a size variable and a pointer that describes a vector. It is a simple enough struct that you can just pass it to a device kernel in any language, and all of the GPU languages are able to ingest some such objects. But we also had to complicate things a bit further to allow us to actually use device-only memory as well. And one other thing that might not be obvious here, but of course, all of the code that I advertise as being device code, that can very well work in host code as well. So as long as you write your algorithms or your functions such that they can be executed in host code as well, you can pretty much just write your code around these types of vectors, and your functions could execute either on your host or in the device. So again, just to give you a little bit of an idea of what code like this would look like. And again, of course, this is nothing meaningful, just something to give you an idea that we would always pass these data types into the in as arguments into, let's say, in this case, a CUDA kernel, and then we would create actual device vector types around these data types. And I only noticed now that I made a typo in the code, but yeah, that's the risk that you run when you just write code without actually checking it. Now, one of the fancy things that we did was that the device code is also able to do some very minimal modifications to the containers. So of course, the device code would always be able to modify the values of elements in containers. That's not a big deal. But our vector types are also able to extend these vectors in device code in a fairly limited capacity. So pretty much what we needed in many of our algorithmic code was to fill vectors in device code, to fill containers with like successful combinations of objects that we found in device code. And we are able to do that to some level. In the current implementation, you still have to choose a maximal size for a container up front, because, well, the device code can't reallocate in the buffer that was allocated. But even this, at least in our R&D examples, seemed to be very useful. Now, of course, all that I've shown so far is not that well. It's sort of fancy, but you could have done all of that with just bare pointers and just some trivial types. The reason that that we opted for this these complex vector types that mimic the interfaces of STL objects is that in our demonstrator code, we want to be able to write algorithmic code that that would not need to know whether it is running in on a host container or on a device container. So we are doing a whole lot of clever templating in our demonstrator code. Here, I was really just trying to flash some stuff, because I have to admit, I myself have not used these types of templates before this, for instance, where we would pass template types as well, template classes as the template types into a class. You can get pretty fancy with this. And so if you are interested in how we are trying to do this, have a look in these higher level projects where we make use of VecMem, while keeping in mind that we are sort of trying to figure this out right now as well. Now, there are also a couple of additional stuff in the project. So on top of these, on these types that manage large allocations in global memory, we also have some helper classes, as you saw earlier, for memory copying and some operations. We have some helper code for expressing atomic operations without writing language-specific code. Some helper code for monitoring what your application is doing, and so on. So, as I said, it's not a huge project, but by now we did end up implementing a couple of things that we thought of as useful things. And yeah, just as finally to show you something where we actually make use of this. And again, this is sort of just to flash this, that one of the algorithms that we had a long time ago, just by turning on memory caching, we could make it perform a whole lot better, at least on an NVIDIA GPU. There, the only difference here is really just how memory is being managed. So with this, again, I was only trying to give you sort of a taste or just a vague idea of what this project is and what we are trying to achieve with this. The main thing that I think in Atlas we are trying to do is to find what will be the new C++ standards, what are the upcoming standards, and then try to write our code already today in such a way that we would be able to migrate to those new standards as they are introduced. Because in the next couple of years, a lot of very interesting things will come to C++ for GPU programming. Now, as I said a couple of times, this is very much our R&D code at the moment. We do have some hopes of putting all of this development into the main Atlas offline software before the High Lumi LHC. And you know, if everything works out, this development that we are doing right now could very well be the core of how we will be writing GPU code for the high-Lumi LHC. And yeah, so if you're interested, definitely get in contact with us. And if you have any questions now, I'm very happy to answer.
Hey, thank you, Attila. It's a very nice overview there, and some very interesting stuff going on there. Do we have any questions?
Yeah,
Jack.
Yeah, hey, this is Jack from NVIDIA. Attila, did you try for your demonstrator comparing to the standard parallel approach of using managed memory?
Well, managed memory. So you really just mean CUDA managed memory?
No, I mean in the stood par parallelism for allowing the compiler to put the memory allocation where the compiler wants to. I mean, they're in the standard in the stood par, as I understand it, there is no concept of memory placement, right? And the committee is implicitly using managed memory.
So pretty much all of the things that we need to implement are, I think we may have tried at one point, but everything that we do is a way more custom than we would be able to express them with STD algorithms. So no, we didn't do this in any serious way, because pretty much anything that we try to do, we have to start writing very custom code very early on for it. So no, I don't think in any of the HEP examples that I've seen so far that anybody would have been able to express any of their algorithms like that.
So I'm not a C++ expert, but if what I understand from the way the standards committee is evolving, that with the stood par parallelism, basically the compiler will choose where to put the information, either on the device or the host. So with your goal of using the standard in the future, it seems like it would make sense to keep track of this now and give feedback if it doesn't work well.
So in the standard, what I myself have a lot of hope for is the generic execution interfaces, because my understanding was that could be a very generic way of describing device code and then choosing where we want to run it. And my hope was that, in the sort of distant future, all manufacturers would start supporting that at one point, of allowing users to write. Not anytime soon, but at one point.
So, I mean, this venue has had sort of the NVIDIA lead, Bryce Lelbach, give a presentation a few months ago about what was going on the standards committee and the stood par parallelism. And we're certainly trying to develop proof of concepts for basically running the same code on host or on accelerated architectures, right, using stood par. So if you're not sort of in dialogue with people who are close to the standards committee, I think it would be a good thing on this to ensure that indeed you're tracking where you want to be tracking.
So thanks a lot. Yeah, I remember that talk from a couple months ago. So should I get in contact with the speaker from that?
Yeah, I mean, I can help you. I'll put my email in the chat and you can get in touch with me. I can connect you with Bryce.
That would be very helpful. Yeah, let's follow up like that. Yeah.
Okay, any other questions? No, okay, I just sort of one very naive one from me, and perhaps sort of connected to what Jack was saying. You say about interfacing with Llama, but my perhaps incorrect impression was that Llama sort of does what VecMem is doing as well, or is it that they're doing slightly different levels?
So, well, Llama, what Llama doesn't do is this memory management part of it, of doing any caching and any of that instrumentation. So I don't know if Martin wants to say more about so I myself was not the one who was talking to the Llama developers about this, but I think, well, we are still trying to figure out what we want to do exactly there, but I think there could be some gains to be made by making Llama able to do its own memory allocations through this memory resource interface. And yeah, we just wanted to try out how that would work.
Yeah. Okay. Sorry, Martin, did you want to come in on that?
Oh no, I was just trying to ask a question.
No, please go ahead then.
Yeah. So perhaps a naive question is how does that the VecMem library compare to Coco's views? Because I see there's could be some similarity between the two concepts.
So, well, as I said at the beginning, both Cocos and Llama, they implement fairly similar things. One of the reasons why we started writing our own thing, apart from wanting to experiment with code, was that we really wanted to make our device code mimic STL interfaces, and Cocos doesn't quite do that at the moment. But yeah, conceptually, Cocos is absolutely doing very similar things, because they are also allowing you to allocate memory through a Cocos data interface on the host, and then pass that object to device code and then do stuff with it. So it is sort of similar.
Okay.
Although I don't know if Cocos does size extensions, or maybe it does, but I don't remember seeing that. So this was one of the things that we added to be able to extend vectors.
Bernhard, just we've got time for a very quick one.
So this is just a comment, since I'm a developer on Llama. Llama tries to focus on data layout and data arrangement, and as far as we can, we try to keep allocation out of the library. So we could very well just interface with VecMem by VecMem providing the storage, and Llama like being put on top to do the data arrangement within the storage provided by VecMem. So we could interface here, but we have like different goals. Yeah, I think.
Okay, no, thanks. That makes sense. No, thanks. Okay, I think as we're sort of over time, let's if there are any further questions or comments, then please obviously follow up in the live notes or offline. So with that, thank you again, Attila, and we'll move on to our second talk, which is I don't know who is presenting today. Is it
me, Ricardo De Maria.
You're going to tell us about the GPU developments in the CERN Beams department.
Yes, actually, it will be a bit more limited. It's not all the Beams department, but actually the Beam group in the Beam departments, Beam physics group in the Beam department. So I will talk about our recent development and status of a bunch of Beam physics code that we have been developing for heterogeneous platforms. So I will start explaining what we do, so which type of simulations we we are doing, the context in which we are developing.
Ricardo,
and,
can you
yes?
fix the sharing, because I don't see the full screen.
Strange.
Maybe stop the sharing and redo it.
Yeah, let me do that. Wait a second, because sometimes just have to put. Okay, now I'll try to share here. No, you don't see anything, and hopefully you see more. Hopefully.
No, I think I've just got your full screen. I'm happy to share, and I can share, and then if you want to just tell me when to go to the next slide.
Is it any better?
No, because it's sort of overlapped with Zoom stuff.
Oh, okay.
So I think
strange. Okay, you could share.
Yeah, if that's okay, just give me 2 seconds to download it, and
yeah, Zoom forced me today to update.
Yes, been there, done that. Okay, could people see that?
I do, at least.
Yeah. Okay, so yeah, just shout out when you want me to move between slides.
Yep. Okay. So yeah, there will be typos, I think, in this version, but okay, never mind. So I will start explaining what we do in the constants which we develop, and in the second half, the technical choices that we adopted in the last year. And I will finish with some question actually to the audience in the sense that I will be interested in knowing what is your feeling about what we do. So let's start. Next slide. So so what we do in many of the beam physics code is we simulate particle trajectory inside the accelerator structure. So the physics that we have, I mean, we start from Newton law and Lorentz force. I mean, very simple. Then we solve electromagnetic problem, and then we add synchronous radiation, particle matter interaction, secondary emission from some surfaces, so things can become a bit more complicated. So next slide. So a first example, for instance, is that we follow one single particle for one turn in the machine, and we want to study the perturbation of the motion around what we call the closed orbit, so the one single periodic solution. Next slide. The next type of simulation in which we track many particles. So here you can see a plot of a section of, you can think of the beam pipe, in which we try to compute how many turns a particle survives given its position in a beam pipe. So this is what we call the dynamic aperture. And this allows us to compute the beam lifetime as well as optimizing the magnet field quality, for instance. So for that, we have to track many particles for many turns. Next slide. Here with PowerPoint, you would see let's say an animation. So the next thing that we do, to complicating a bit, is to simulate how many interacting particles also interact within themselves and within the boundary, the surfaces of the vacuum pipes. So this basically couples beam trajectory simulations with the electromagnetic solver. And next slide. Also here you would see a nice movie. We also then simulate how the particles can, for instance, drive electrons far from the surfaces and interact again electromagnetically with the beam. So where things becomes even more complicated. So next slide. So now, why GPU computing, why accelerator matters for us is that so if you got, I mean, some ideas of this simulation, is that there are some type of simulation that are embedded in parallel, often without branching. For instance, the simulation on dynamic aperture. So this is this plot shows an example of this, in which we want to apply the same algorithm for a long time for many particles. So, but also for more complicated simulation, for instance, electromagnetic solver, there we have F50-based algorithms that scales also well with GPUs. So to give an example here, I put on the left how the computation time scales with the number of particles for CPU and GPU. So you can see that, of course, a single core scales linearly. So the more the more particles you track, the more you have to wait. With GPU, so things goes in parallel, and the parallelism scales really well up to 20,000 particles, for instance, for every 100, and then you start to see the linear increase again. If you see quantitatively, so there are order of magnitude, so there are 2 order of magnitudes gain within 1 core and 1 GPU. Now, realistically, with the resources that we have, we can see that we can even more, because everybody is using CPU and not so many today using GPUs. So for the same simulation that in the HT Condor cluster takes 7 days for, let's say, 1 second of simulated machine, using GPU in the same HT Condor cluster, it takes 24 hours, but for 10 seconds. So we get on really realistic load 70 times more, so 70 more results using GPU platform. And this is why we are investing a lot on it. So next slide. So now, how we do development in ABP? So what is the context? So in general, the codes needs to be continuously tailored for specific studies. So we could write the most complex generic code, but this would be too slow for many applications. So very often we really try to identify what are the meaningful features that we have to simulate and simulate only those. So we have a continuous development. So in terms of development time, normally we don't have people dedicated to computing. So staff develop part-time, sometimes few weeks a year. Most of the time, maybe more in certain cases. So student fellows often doesn't come with strong computing background. So we normally have students with a physics background and with experience on the problem rather than on the tools. And in addition to that, the numerical methods that we use in the field are also not very well documented. So sometimes to re-implement an algorithm takes a lot of time, because one has to understand what has to be done, debugging or reverse engineering existing code rather than looking some well-documented paper. In general, we need a high throughput. So we need a lot of results, because we often have to study large parameter spaces. But also we need low latency in certain cases, because in certain situations, for instance, when running a machine, we have to do simulation that gives us a quick answer to take decision of what to do the next day, for instance. So we cannot wait months to get an answer. And GPUs provides, in general, more resources. So even if we could run on CPU, GPUs gives additional resources for free almost, and also enable computation that are otherwise not possible. So 70 times more, it means that certain scans can be done rather than not. So this context translates in this requirement. So we need a rapid development environment based on a popular and simple programming language with large library ecosystem to code the least possible. We want that the code is run immediately on NVIDIA, AMD, and Intel GPU, because this is the hardware that we have available today. And in our machines, I mean, the user machine locally, or I mean, every laptop has a quite capable GPU today, and it's a pity not to use it. And also in data centers. So we cannot wait the next framework to appear. And then also the first implementation really needs to achieve close to maximum performance, ideally. I mean, because often we don't have time for optimization. We don't rewrite the code very often. I mean, sometimes also the code is written for one specific study and then thrown away. So we want to have as soon as possible maximum performance. So next slide. So this is what we came up with starting from 2021. Actually, I mean, we embarked in a large code refactoring. So we decided to organize the new code in Python packages. We assume that Python scripts drives the user interaction with the code. So people that want to use the code has to write Python scripts. So data structures are described in Python, allocated in Python, and fully exposed in read-write mode in Python, including on GPU. So we want to avoid unnecessary copy to with CPU, I mean, from device and host. So we want that, let's say, we want to work most of the time on GPU if possible. So the performance critical code would be written in C, thanks to an automatically generated CPI from Python for interacting with the data structure. We also need and want the code to be able to be compiled at runtime and on demand. So this for us is essential because in particular in GPU, there are specific optimization that are fitted only for one specific problem. So it would be too expensive to compile all possible combination of problems, and it would be too expensive to use the most generic implementation, because in GPU, even the code that where the code that you don't use still can cause a suboptimal allocation of the resources. And then we want to have also reduce a cycle between writing, testing, and executing the code. So it's nice that we can change an algorithm on the fly while having the memory live in the GPU, so without stopping and restarting again. So in terms of dependencies, we decided to be as little as possible. So NumPy to allocate and exchange memory on the host. CFFI with an installed C compiler used under the hood to generate binary pattern modules that can be imported at runtime and also to prepare the arguments for functions in the CPU. CuPy and of course the CUDA driver to implement, let's say, to use the CuPy array, but also again to allocate and manage the memory on the device and to compile CUDA kernels. PyOpenCL and of course some OpenCL driver to implement, let's say, to use again the NumPy-like array provided with the library, as well as managing memory and compiling kernels. So next slide. So talking about OpenCL, so why we are targeting OpenCL? So the targeting OpenCL, I mean, is a precise decision, although of course it constrained the device code. So we are forced to use C instead of C++. It's not the only reason why we like C rather than C++. The other is that it's simpler to understand also from people that don't have a C++ experience, and there are more people, let's say, that do not know C++ than do. Then the other reason is that OpenCL 1.2 has been stable and supported since 2011, so it's a lot of time. It works well, still continue to work. Doesn't offer all the potential optimization that you could do it with CUDA and maybe with the heap or cycle, but anyway, we would not have too much time for it. And then practically any hardware has both a proprietary and an open source implementation of OpenCL. So this, I think it tells us that the OpenCL framework will not disappear very soon, even though vendors are pushing strongly towards CUDA, towards heap, towards cycle. And then you can also see that even if you support CUDA, heap, and cycle, which is a lot of effort, still you have red boxes. So you don't have access to certain hardware, which we think is a bit of a pity if it is available. Okay, so for us, let's say OpenCL is still the best protection against vendor lock-in. So this is what drives, let's say, our choices to support it, at least in parallel to CUDA. Next. So what is the status after 1 year of development? So you saw, so we have a bunch of libraries that we use to interface with the devices. Then we wrote a Python package that we call XObject that guess what, manages memories and as well as computation. And then we wrote the physics part based on X objects on separate modules, let's say. So in this way, we separate the memory management and the data structure management from the actual physics. So in terms of resource invested, so for this infrastructure, we dedicated 2 developers for, let's say, the equivalent of half FTE. And then for porting the existing code into the new structure, again, 2 developers and a few days of about 5 experts for another half FTE. To give an order of magnitude, we now managed to, let's say, move in 1 year about 20 users to the new codes. So they were happy to do the switch for the increased performance and increased, let's say, flexibility thanks to Python. In terms of lines of code, let's say we implement the equivalent functionality of 150,000 lines of code in about 10,000 lines of code for the coding itself, and another half for tests and examples. So of course, this shows somehow that most of the codes, of course, have to deal with the user interface and writing many low-level parts that we could auto-generate, and other things we just removed thanks to the fact that Python could offer either libraries or let's say a nice scripting environment that doesn't need, let's say, all the features that were available in the old codes. Okay, next slide. So just to give a glimpse, I would go very fast here. So we have this infrastructure. I mean, this middleware basically is based on a layer that goes from an object that is that manages memory. So it's a byte blob with a memory allocator that it is built for CPU using NumPy or OpenCL or CUDA using CuPy. Then we have an object dealing with kernels, so compilation and execution, a context that somehow connects the two, and also compiler settings for the CPU, or an OpenCL context for OpenCL, or the CUDA device for CUDA. And on top of that, we added a set of objects that allows to build a data structure in terms of building blocks. So you have a structure, an array, a reference, a union, and then the C API generator. Next slide. So how things looks like. So you write, let's say, your data layout using these building blocks on the left, you can see. Then you define a context, whether it is GPU, CPU, and so on, and then you can populate the data using Python, for instance, and then you can see that you can get read-write, let's say, access in a simple way to the device. So this is all hidden due to thanks to the library. So go back, next slide, sorry. So then once data structure is defined, then there is the C API generator that creates a lot of functions that are basically accessor functions. So to get in the C part, both I mean on the CPU or on the device, the pieces like the numbers, like the double in an array, or to set it, or to get pointers to those parts. Next. And then one can directly write some C code, or even in a string as it is, to use this, I mean, to interact with this data using this C API. So this, for instance, is a loop that it's actually C code that you can compile yourself. So we decorate this C code with some special comments that allows us then to recognize the piece that we want to change. Next slide. To adapt to OpenCL, for instance, next slide, or CUDA. And then let's say once you write this code, then you can compile in the same Python process and execute right away. So next slide. To see a bit low level what happens, so you can see that let's say for instance, this is a case of an array of structure. You can see that this accessor function on the lower left side let's say, gives, I mean, you can compile, let's say, a function that find the location of the memory referred by the indexes, for instance, and offer a way to extract it. Then the way this API is designed is that in case of change of structure, actually the API doesn't change at all. So we try to make sure that if you do a change between array of structure of array, or structure of array, and so on and so forth, you keep the same API. So we spend some effort in trying to make sure that then the physics code that you could write most of the time doesn't need to be changed if you change some type of structure, let's say. Next slide. So this it's already the conclusion. So for us, the GPU allows us to have access to additional computing capacity, and also enables new computation that otherwise would be prohibitive. So of course, developing portable code is extremely challenging. I think, still today we have multiple incompatible languages and frameworks, and I think vendors are not really helping our life, but rather increasing fragmentation. Now we have, 3 frameworks, 3 vendors. So I think this is not helping. Although, it's nice that they are at least converging on C++, but still, I think there is a lot of work to be done to stabilize the new frameworks. So for us, the situation is not ideal. So given this context, in ABP, the Beam physics group, we decided to leverage Python and the ecosystem for the user API, and also for low-level code to do C code generation. So we saw at the end that with C code, we could target all the devices, and then we prefer to write our own, let's say, low-level generation rather than waiting for the C++ frameworks to emerge. So with this, we can support today OpenMP, CUDA, OpenCL, and cover all the hardware that did exist. And for the moment, we managed to obtain the performance that our initial effort with GPU code got us. So it's equivalent to handmade code. And we also managed in 1 year to have the functionality coverage that we wanted. So now, having seen that, so this is more question for the audience, and also to drive a bit of discussion if there is time. So is this approach future-proof? So we believe that with some control, since we control the API and the data structure from Python, we could also generate code that can use that. Still is a bit, future is the future, we don't know yet. So I think the other important question is we will manage to keep the cost of the framework low for as the code become more complex. So this is also is another question. So as you could see, we are not rewriting a full compiler, but in some cases it's almost what we are doing. So of course we focus on exactly what we need on the data structure that we need, but I think what we are afraid is that we will not be able to cover all cases easily. And then the next question, are we really maximizing performance given the effort? So is there alternative ways to achieve that? So to be able to program quickly for all the devices that are available. So for us, the approach is using C++ framework were too heavy at the moment. So that is why we decided on this way. But maybe this is not the case. So this would be, I think, nice to hear your feedback on this. And that's it.
Okay, thank you very much, Ricardo. Very nice talk. I see we already have a question from Attila.
Yeah, I have to admit, I'm a little bit confused about the messaging here. So you made a big point about OpenCL being such a good interface for you guys, but then why don't you embrace it? Why do you still do this abstraction on top of OpenCL? I thought that, well, if you go OpenCL, you go OpenCL and you let that code run everywhere, because technically it can, as long as you can express your algorithm in standard C, yeah, that could work.
So there are 2 reasons. So one is that we are afraid, as everybody, that OpenCL will disappear. So I think if you talk to vendors, I strongly encourage to not to consider OpenCL. Okay, reality is different. Reality shows us that this is not longer the case. I mean, this is not the case today, at least. But can we trust that? So I think this today, I mean, I think it was April 2021 when Mesa, for the first time, almost completed OpenCL 1.2. So for me, this was a big, let's say, encouragement in continuing on OpenCL. I haven't tested it, so I don't know if this is performant or not. But at least this is an encouragement. However, we are still relying on vendors to provide an OpenCL interface. If they drop it, we are on the yeah. I mean, we want to be able to run. Next is that if we are able to use OpenCL and CUDA, somehow this also tells us that our approach is portable also for the future. So if there is a next environment that brings us more, OpenCL, I mean, it doesn't give you the degree of controls on the device that CUDA offer, for instance. So there are many optimizations that we cannot do it. At the moment, we didn't need it, but I don't know, maybe it's just temporary. So I think for being future-proof, I think we have to prove that we can support another environment, I mean, another framework. That's the reason.
So organization-wise, do you think that all of the algorithms that you need to implement, you would implement in just one way and then run that on any backend? Because for context, in many of the problems that we are trying to solve, we pretty quickly found that the most efficient algorithm is just not the same on a CPU and on a GPU. And at that point, all of this abstraction of, well, let's describe it in one way and then be able to run it either on a CPU or on a GPU is sort of wasted effort, because the GPU code just runs very slowly on a CPU.
Yeah, so it is true, it is correct. And to defend ourselves on this is what we did is to make sure that we could change under the hood the memory structure at least without changing the API using this memory structure. So these allow us, for instance, to at least exchange structure with arrays and vice versa without, let's say, easily. So what I could see is that for certain algorithm, you could have a data structure for the device and a data structure for the host, although they would share the same code. But for the most complex case, I mean, when you have to deal with the data structure that are not simple, let's say, meshes where you have trees or graph and so on, I'm afraid that you inevitably you need algorithm that has to be, let's say, adapted. And on this side, I think the fact that we can compile quickly and choose the algorithm also at runtime will help. I mean, there are certain algorithms that simplifies a lot if you really target to the problem. And so by analyzing the problem, you can then change the code on the fly to adapt to that. So also this is another lines of defense.
Okay.
Yeah.
Okay, thanks.
I don't know, I mean, if this answered the question, but yeah, so we don't try to really write, I mean, we don't enforce that the code has to run, to be the same, but we try to put ourselves in a position which we can reuse at least most of it.
Giovanni, did you want to come in, or did you have a question on?
Yes, mostly a comment on this point of why not fully OpenCL, let's say. So let's say if you want, Ricardo was working a bit on on the underlying piping, and I was doing more the application side on top. I mean, if you want the physics. So on one hand, we have, let's say, a lot of, let's say, code that is the tracking code, let's say, that we really write in C. When you move a bit more to collective effects, there the algorithms become a bit more, let's say, if you want, complex, which has the advantage that you can reuse libraries, basically. So that chunk of code, in fact, ends up being written in pure Python, if you want, in the sense that you are just using cuba arrays for linear algebra and this kind of operation, and FFT called directly from Python. So you are operating on data structures that are so big that actually you don't need to get inside the compiled code. You're just saying, please make me the FFT of this 1 GB matrix, for example. And there, of course, the offer that you get from Kubai and from the CUDA, let's say, kind of ecosystem is another level compared to what you get from OpenCL. So reality was that I got the Kubai working, let's say, nicely in an environment where I could move freely. I mean, everything was behaving very nicely. And then when I got something that would work, I hammered OpenCL until it did the same by patching here and there, basically. So we managed to get OpenCL to work, but it's not definitely a comfortable environment to work with when you are moving away from very basic algorithms that are writing yourself, but you want to get libraries in the picture, let's say.
Yeah, thanks for the background on this.
Actually, I don't know, Jack, you made a comment in the chat about NVIDIA drop-in for NumPy. Did you want to say anything about that?
Just to say it's available. NVIDIA very much wants to support Python as a high-level language and is continuing to invest in these libraries so that people can easily move from the code that they would use on their usual development system into a distributed memory parallel computer. So it was a new announcement. This library called cuNumeric.
Yep, that's very interesting indeed. So I think today we use CuPy because it was the most advanced, let's say, NumPy-like library that we could find. We also saw that NVIDIA provided a native CUDA interface to also compile kernels and allocate, to, let's say, low-level memory management directly on Python. So at the moment we were using CuPy because it was putting everything together easily and nicely. Let's say there were many low-level things were already implemented in CuPy. I didn't know about cuNumeric, so it's good to, thanks a lot. We will look certainly into that.
Yeah, to add on to that, cuNumeric actually includes utilities that are based on the programming model you may be familiar with called out as Legion. So you actually, not only do you get a Python interface, but it is set up with utilities that will allow you to be able to run in parallel with a task-based parallel programming model. And that comes along with the cuNumeric package. So to the extent that would fit your problem set, that's another benefit to the approach.
Yep, thanks a lot.
Sure.
Okay, any further questions? No, I just had one perhaps more very general one. Again, coming back to this challenge of future-proofing and cost of the framework. I'm not sort of in the sort of community of beam physics, but is the sort of sharing between labs, or is the technology, let's say CERN versus Fermilab versus JLab and anywhere else, so different that you really can't use the same software framework, or do you have any scope for sort of collaboration and sharing that way, if not already?
At the moment, this effort started beginning of this year. So at the moment we are, let's say, it's not, a proof of principle in the sense we ported real code and we are using this code in production and we are filling queues. We are getting results. So, and I think, our approaches to that is that if people are interested, they are most welcome to jump in. We want to rather prove that the framework is worth it by providing results and fast code, so and functionalities. So we are seeing that many, I mean, we are seeing interest outside our, let's say, group, because I think people are seeing that we can provide quickly codes and implementation. So this we will see. At the moment, there is no, let's say, no established collaboration, if you want. Of course, it would be fantastic if we could share the work. However, I see that it's always difficult. What I see, I mean, the problem that I see happening, for instance, in high energy physics, when I looked at the work done here, is that I think the focus of the people working there is more oriented for the future. And all the time I hear statements that saying that we are, let's say, preparing for, let's say, the compilers to be ready and the hardware to be ready. So it seems that the scope is more, it's more far on the future. On the other hand, we need the codes to run today. And so that is why I think the focus is a bit different, and we will not be able to profit from the effort, I think, if we want to run today on AMD. So for instance, Cocos is not ready, or HEAP doesn't target all the hardware that is we have it around, for instance. Or Cycle, there are still issues with the compiler at Intel. I mean, we tried, but I mean, we spent, I mean, the first compiler bugs we saw, we abandoned because we cannot spend time in let's say, helping the development of the compiler.
Yeah, your time scale for getting results is a bit different, definitely.
So I mean, we need it now. I mean, we need something that, because the hardware is there, right? And indeed, we are happy somehow that there are not so many codes profiting from GPUs, because we can harvest everything that CERN can give us.
Yes, a good position to be in. Okay, thanks. Okay, so if there's no further comments or questions, I think we can close here. Obviously, feel free to follow up with any comments or further questions on the live notes. And of course, the meeting is recorded as well if you want to revisit anything. But with that said, thank you again to our speakers for some very interesting talks, and thanks everyone for the discussion and participating. So with that note, the meeting is closed, and as I said, I hope you all have a great holiday and New Year, and we'll reconvene in 2022 in February. So thanks everyone, and goodbye.
Thank you. Bye.
Bye-bye.
Bye.